The future of in-orbit spacecraft refueling and servicing is poised to become one of the most transformative advancements in the space industry. As more satellites and spacecraft are launched into orbit, the need for sustainable and long-term operations becomes increasingly critical. Traditional spacecraft are designed with a finite operational lifespan, dictated largely by the availability of onboard fuel and the reliability of their components. Once they deplete their fuel or suffer a malfunction, these satellites become space debris, even if they are otherwise functional. This limitation significantly impacts the efficiency, cost-effectiveness, and environmental sustainability of space missions. In-orbit servicing and refueling technologies aim to solve this by extending mission lifespans, enhancing operational flexibility, and enabling a new era of reusable and upgradable space assets. In-orbit refueling involves transferring propellant from one spacecraft to another in the vacuum of space. This concept, once confined to science fiction, is now being actively pursued by both governmental space agencies and private companies. The technical challenges are immense. Spacecraft must align precisely while traveling at thousands of kilometers per hour, connect fuel lines in a zero-gravity, vacuum environment, and handle highly volatile propellants with utmost precision. Despite these challenges, several successful demonstrations have proven the viability of this concept. NASA's robotic refueling mission, conducted aboard the International Space Station, demonstrated techniques for transferring cryogenic and pressurized fluids between simulated spacecraft. The Defense Advanced Research Projects Agency, DARPA, and commercial firms like Northrop Grumman and Orbit Fab are also investing heavily in these capabilities. Orbit Fab, for instance, is developing a fuel depot system for low Earth orbit, dubbed Gas Stations in Space, that aims to provide standardized refueling ports and tankers for commercial and governmental customers. Their RAFT, Rapidly Attachable Fluid Transfer Interface, refueling port is designed to become an industry standard, allowing future spacecraft to refuel without custom adapters or retrofits. These depots will enable spacecraft to extend their missions beyond initial design parameters, adjust orbits for mission changes, and even undertake entirely new roles after their primary missions are complete. On the servicing side, advancements are being made in robotic arms, autonomous navigation, and modular spacecraft design. Spacecraft servicing includes tasks such as repairing malfunctioning components, replacing outdated hardware, upgrading sensors or communication systems, and even relocating satellites to different orbits. Northrop Grumman's Mission Extension Vehicle, MEV, is a notable success in this field. MEV-1 successfully docked with a commercial communications satellite in 2020 and extended its life by several years by taking over its propulsion and navigation functions. MEV-2 followed with a similar mission. These milestones underscore the feasibility and commercial value of servicing missions. The evolution of modular spacecraft design complements in-orbit servicing. Satellites built with replaceable parts or standard docking interfaces can be upgraded or repaired more easily. NASA's OSAM-1 on-orbit servicing, assembly, and manufacturing mission is a prime example, aiming to refuel a government satellite and demonstrate assembly of large structures in space. The ability to construct and modify spacecraft on orbit opens possibilities for building large, complex systems such as space telescopes, habitats, or solar power stations without launching them fully assembled from Earth. In-orbit servicing also facilitates debris mitigation. Many current missions involve spacecraft that are perfectly functional aside from propulsion failure or minor damage. By repairing or refueling these assets, agencies can reduce the volume of orbital debris and make better use of existing hardware. Furthermore, servicing spacecraft can deorbit defunct satellites safely, contributing to long-term orbital sustainability. Refueling and servicing will play a critical role in deep space missions as well. Missions to Mars or beyond require vehicles with long-duration capabilities. Instead of launching massive tanks of fuel from Earth, missions could refuel at depots in cislunar space or on the Moon, leveraging resources extracted from lunar regolith or asteroids. This approach is aligned with the principles of in-situ resource utilization, ESRU, where local resources are converted into usable materials like water or propellant. Combined with robotic servicing technologies, this could enable long-duration missions with flexible timelines and reduced launch mass. The development of servicing infrastructure requires standardization across the space industry. Universal docking ports, standardized fluid connectors, and interoperable data and power interfaces are essential to make refueling and servicing broadly applicable. Agencies like NASA and ESA are working with industry partners to define these standards. The adoption of such standards will pave the way for a plug-and-play space ecosystem where spacecraft from different manufacturers can interact seamlessly. One of the most exciting prospects is the potential for servicing-enabled commercial platforms. Space stations, large telescopes, and orbital factories could all benefit from periodic maintenance and upgrades. This would shift the paradigm from disposable space assets to long-term, maintainable infrastructure, akin to terrestrial utilities and transportation networks. These platforms could host human crews or operate autonomously, depending on mission requirements. Technological advances in autonomous navigation, artificial intelligence, and robotic dexterity are key enablers of in-orbit servicing. Future servicing spacecraft will need to identify, rendezvous with, and dock to client satellites with minimal human intervention. This requires sophisticated sensor suites, real-time decision-making algorithms, and highly reliable control systems. Machine learning techniques are being developed to improve autonomous operations, including adaptive control systems that respond to unexpected changes in spacecraft behavior or environmental conditions. The economic implications of in-orbit servicing and refueling are profound. Currently, satellite operators must design missions with the assumption that once a satellite is launched, it cannot be modified or refueled. This drives conservative designs with significant cost buffers. With reliable in-orbit servicing, operators can reduce upfront costs, shorten development timelines, and take greater risks in technology deployment. Moreover, the ability to extend satellite lifespans increases return on investment, particularly for expensive assets like communication satellites or Earth observation platforms. Regulatory and policy frameworks will need to evolve to support these new capabilities. Issues such as liability, ownership rights of serviced satellites, and coordination of orbital traffic must be addressed. International collaboration and transparency will be critical to ensure safe and equitable access to servicing infrastructure. Spacefaring nations and companies will need to develop norms of behavior, licensing procedures, and conflict resolution mechanisms to manage the complexities of a more interactive orbital environment. As private sector capabilities grow, the landscape of space logistics will increasingly resemble terrestrial models. Just as highways, gas stations, and repair garages support long-distance travel on Earth, orbital highways, fuel depots, and service vehicles will underpin sustained space operations. The development of a space logistics network will support human exploration, satellite constellations, space tourism, and even asteroid mining. In-orbit manufacturing and assembly will further enhance the value of servicing missions. As structures are built in space, they will require inspection, maintenance, and adaptation. Robotic servicing vehicles could install new modules, reposition components, or repair damage from micrometeoroid impacts. The synergy between in-orbit assembly and servicing is expected to catalyze the development of large-scale infrastructure, such as solar power satellites, radiation-shielded habitats, or next-generation observatories. Educational and workforce development must also keep pace with these advancements. New disciplines in space engineering, robotics, fluid dynamics, and orbital mechanics will become increasingly important. Universities and training programs must adapt to prepare a new generation of engineers and scientists equipped to design, build, and operate servicing and refueling missions. Public-private partnerships and internships with space companies will play a key role in developing this talent pool. Furthermore, the environmental impact of space activities must be considered. While in-orbit servicing can reduce space debris and enable sustainable satellite operations, the servicing vehicles themselves must be designed with responsible end-of-life plans. This includes the ability to deorbit, relocate to graveyard orbits, or be refueled and reused for future missions. Sustainable servicing practices will be critical to maintaining a safe and usable orbital environment. Looking ahead, the convergence of robotics, AI, propulsion, and modular design will transform space operations into a dynamic, service-based economy. Satellites will no longer be static tools launched for single-purpose missions, but will evolve into adaptive platforms that change and grow with technological advances. Space agencies and private enterprises are already investing in this future, laying the groundwork for an orbital ecosystem that mirrors the complexity and interdependence of Earth-based industries. From reducing costs and waste to enabling ambitious new missions, in-orbit refueling and servicing represent a cornerstone of the future space economy. Their success will depend on continued innovation, collaboration, and vision, qualities that have always defined humanity's journey into space.